Welcome to the One World Combinatorics on Words seminar. Our speaker today is Kaisei Kishi from Kyushu University, and he is going to speak to us about net occurrences in Fibonacci and Thue-Morse words.
Thank you for introduction. I'm Kaisei Kishi. I'm a doctor of Kyushu University. Today I will going to talk about the net occurrences in Fibonacci and Thue-Morse words, and this is the joint work with Pika, who is the assistant professor of Institute of Science Tokyo and studied in the University of Melbourne. First, I will define the Fibonacci words and Thue-Morse words. We define the case Fibonacci words Fk as follows. F1 equal B and F2 equal A. And when k is greater than or equal to 3, Fk is defined as the concatenation of Fk minus 1 and Fk minus 2. For example, F5 is AB, and this is the concatenation of ABA, which is F4, and AB, which is F3. And we define the smaller Fk is the length of the Fk. And this is the case Fibonacci number. Next, we define the Thue-Morse words. The case Thue-Morse words Tmk is defined as follows. Tm0 is A, and when k is greater than or equal to 1, Tmk is defined as the concatenation of Tmk minus 1 and Tmk minus 1 bar. And we can get Tmk by replacing all A and B in Tmk. For example, Tm3 is ABBA, and this is the concatenation of ABBA, which is Tm2, and BAAB, which is Tm2 bar. And we define that tau k is the length of Tmk. Next, we define the net occurrence. The occurrence of the substring S of S in T is a net occurrence if S is repeated in T and both the left extension and the right extension of S are unique in T. For example, there are 3 occurrences of THE in the T. And among these 3 THEs, these 2 occurrences of blue THE are not net occurrences because the left extensions of the blue THE is both under bar. This means that the left extension of the blue THE are repeated in T. This means that this occurrence of blue THE is not net occurrence in T. On the other hand, this green THE is a net occurrence in T because the right extension of THE is THE under bar, and this THE under bar is unique in T. And note that we assume that the left occurrence of the left extension of the occurrence of prefix to be unique in T. So this green THE is a net occurrence in T. Next, we define the net frequency. Net frequency of substring S in T is the number of net occurrence of S in T. For example, there are 3 occurrences of THE in the T, and we show that these 2 occurrences of blue THE is not net occurrences, while this green occurrence of THE is a net occurrences. So NF of THE is 1 in T. And when we see these net occurrences, only green THE is used as a definite article, the. And while other blue THE is used as prefixes of other words, such as theoretical and theme. This means that the net frequency of S focuses on the importance occurrences of S in T. And originally, net frequency is motivated by Chinese natural language processing tasks. And it is expected to be applied to such fields, such as making corpus. And we show some recent works. There are some algorithms that compute the net frequency in offline settings and online settings. Also, Mieno and Inenaga in 2025 characterized the net occurrences in terms of the minimum unique substrings, MUS. Next, we will show our works on the net occurrence in Fibonacci and Thue-Morse. We proved that these all 3 colored substrings of occurrences are the net occurrences. And we proved that all other occurrences of the substrings are the not net occurrences of Fibonacci words. And about Thue-Morse words, we proved similarly. That is, all these 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 occurrences of substring of substrings are the net occurrences in Thue-Morse words, and other occurrences of substrings are not net occurrences. And in order to prove this, we will show some basic properties of net occurrences. The first is that the super occurrences of any net occurrences is not net occurrence. For example, we showed that this green THE is net occurrence. And when we see that the occurrence of THE underbar, this must not be a net occurrences, because since this green THE is a net occurrence, so the extension is unique. So this THE underbar must be unique. So this occurrence of THE underbar is not a net occurrence. The second occurrence, second property is like opposite, which means that the sub-occurrence of any net occurrence is not a net occurrence. for example, this green occurrence of TH is a net occurrence. And when we see the occurrence of TH, no, sorry, HE, this is not a net occurrence because HE occurs repeated in T, but the right extension or left extension of HE must be repeated in T because THE, this green THE is a net occurrence in T. Therefore, this occurrence of HE must not be a net occurrence in T. By using these properties, we can reduce the number of occurrences that need to be examined. So that we prove that these three substring occurrences of substrings are net occurrences, and I said that we proved all other substring or occurrences of substrings are not net occurrences, but in fact we only to prove that only only these only the occurrences which shown in the super occurrence of these colored arrows are not net occurrences. For example, this pink arrow shows that the occurrences of the super occurrences of Fi minus 4Qi. So this is longer than this uh, dotted line and longer than this dotted line. And this pink arrow can be longer than here or here, but must be inside this dotted line because if pink arrow is longer than this dotted line, this must be the super occurrence of the Fi minus 2Qi. So pink arrow cannot be the net occurrence. So we only have to think that the pink arrow is outside Fi minus 4 Qi minus y and inside the Fi minus 2 and Qi. We can say similar thing for blue arrow. And also we proved similarly for the Thue-Morse words. So we proved that all the nine occurrences of substrings are the net occurrences, and the all occurrences showing these arrows are not net occurrences. And next, we will show how to find the net occurrences. To confirm the occurrence of substring T is a net occurrence in T, we have to prove that the substring of T is repeated in T, and right and left occurrences is unique in T. And we in all so in general it is difficult, but if we can count the number of occurrences of all the substrings T in T, we can prove these things easily, and therefore we can find all of the net occurrences in T. So next we'll briefly explain the proof of the net occurrence in Fibonacci and Thue-Morse. So we proved that these three strings are net occurrences, and these are substring of arrows are not net occurrences, and we proved this by carefully counting the number of occurrences of substrings. For example, we proved that the substring of pink arrow is not a net occurrence because, in fact, this when we extend from dot line from one length and extend from the left dot line with one length, the pink arrow becomes unique in Fibonacci. So therefore, the longer pink arrow is also unique in Fibonacci. So this means that the substring of showing the pink arrow is not a net occurrence in Fibonacci. And we count the number of occurrences of substrings in Thue-Morse similarly. And in order to count the number of these substrings, we characterize the occurrences of the smaller fj and tmj in the bigger fi and tmi. And next we will introduce how to characterize these occurrences. So, by the definition of the Fibonacci words, Fi can be factorized into Fi minus 1 and Fi minus 2. And recursively, Fi minus 1 can be factorized into Fi minus 2 and Fi minus 3. And so therefore, these strings can be factorized into Fi minus 3, Fi minus 4, Fi minus 3, Fi minus 3, Fi minus 4. And when we factorize these substrings again and again, Fi is finally factorized into Fj plus 1 and only with factors of Fj plus 1 and Fj, like this. And when we characterize the occurrence of Fj in these strings, since there are only 4 cases of occurrence of Fj in Fi, that is that Fj occurs inside the Fj, and Fj occurs inside the Fj plus 1, and Fj occurs across the border of Fj and Fj. This is the inside of the Fj and Fj plus 1, and Fj occurs across the border of Fj plus 1 and Fj, and Fj plus 1 and Fj. This is here. So by dividing these cases, we can easily check that how many fj occurs in each cases. So fj occurs only once in fj, fj occurs only once in fj plus 1, and fj occurs only twice in the fj, and fj occurs only 3 times in fj plus 1 fj. So therefore, we can characterize all the occurrences of fj in fi. So these uh, occurrences of fj is all the occurrences of fj in fi. So for the Thue-Morse words, we characterize the smaller occurrences of TMJ in TMI similarly. So TMI can be factorized into TMI minus 1 and TMI minus 1 bar. And also this TMI minus 1 and TMI minus 1 bar can be factorized into TMI minus 2 and TMI minus 2 bar like this. And when we repeat factorizing that, finally we can factorize the TMI with only using factors of TMJ and TMJ bar like this. So, and since this is there is a famous theorem that Thue-Morse bars has no overlapping occurrences of the same strings. So Thue-Morse bars is overlapping free. So we can easily characterize all the occurrences of TMJ in TMI. And this colored TMJ is all the occurrences of TMJ in TMI. For example, uh, pick, so TMJ might occur in here, but this cannot be because TMJ is not equal the TMJ bar. Also, TMJ can be occurred within the other TMJ, but it is not cannot be because uh, this TMJ overlaps with other TMJ. So these colored occurrences of TMJ is the only occurrences of TMJ in TMI. So these are the how to characterize all the occurrences of Fibonacci, smaller Fj and TMJ in bigger Fi and TMI. So this is a conclusion that we briefly introduced the net occurrences and net occurrences and net frequency and some properties of net occurrences. And we showed that the characterization of the occurrences of the smaller Fibonacci was Fj and smaller Thue-Morse was TMJ in the bigger Fibonacci was Fi and Thue-Morse was TMI. And we briefly showed the proof of that there are only 3 net occurrences in Fibonacci world and there are only 9 net occurrences in Thue-Morse world. And about the characterization of occurrences of Fibonacci words and Thue-Morse words of smaller order, uh, Mr. Jeffrey provided the alternative proof using walnut. So we will briefly explain the walnut. So walnut is a free software that uh, has been used to prove and disprove many theorems and combinatorics on words. And sorry, 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 I forgot to say how to. Sorry, forgot to say how to say next, so I skip the next content. So and now, and so Mr. Jeffrey showed alternative proofs, and I and my coworkers, Mr. Pika, get interested in. So now, and we and Mr. Jeffrey have been studying the net occurrences. Uh, so the occurrences of smaller order and the net occurrences in other automatic sequences, like other morphic words. And finally, we talk about our future works. So that is the characterization of the smaller order occurrences of other works, of other words. And I think these works can be done by Walnut or uh, some theorems like of morphism, like the recognizable morphism. And other future works are the net occurrences of other morphic words, like Fibonacci words and Chimos-like words and other morphic words. And I think these future works we can be done if we can characterize of the other of small order occurrences of other words. Uh, Thank you for listening, and I'm sorry for my poor presentation.
Thank you very much, Kaisei. Really
Thank you.
great talk. Does anyone have any questions? Hajime.
Oh, thank you for a nice talk. And so you considering the future work of other morphic verses. So my question is about so as a generalization of Fibonacci word. So is it possible to consider other Sturmian words? Sturmian words.
Yeah, I know. I think it's not easy as a Fibonacci words, but I think we maybe can. But I think it seems to be difficult. Yeah.
Thank you.